Okay, so now we will discuss about the kinetics of the slider crank mechanisms. In this case, this is again the same diagram. Now in this case, to discuss kinetics, we will neglect friction between the cylinder and piston. We will also neglect gravity. So this means uh, that there will be no gravitational force here. And again, we will assume that the mass of the connecting rod is zero here. So we will neglect the mass of the connecting rod. Uh, okay. So as you can see in this case here, that the as you know that the P here is the so for this case, if you want to draw the free body diagram for the piston part here, so which will be something if you consider this piston here. So this is the piston, and now in this case there will be some pressure from the combustion gases which is on this side of the piston here. So if you consider an engine, and the force will be P, which is the pressure times cross section area of the piston here, and mass of uh, this piston is M here. Now we know that the you consider this point here. So we know that that this force, which you can call this F1. So F1 here uh, is the is the force exerted by the connecting rod on the piston, and you can also then consider another force on the piston, and you can call this F2. So F2 is the force exerted by the cylinder wall on the piston. And the acceleration of the piston is going to be in this direction, so which is x double dot, and this angle is phi angle here, and the force F1 is along the connecting rod, and because here we are ignoring uh, the uh, the mass of the connecting rod, so the force is going to be in the direction of the connecting rod here, and F2 is the force of the cylinder wall, and PA is the force of the which is applied by the combustion gases on the cylinder on the piston here. So these are the main forces that we will have on the piston here. And again, you can draw the free body diagram. So you can take this is our x direction, this is our y direction here. Okay, so now in most cases, P, which is this P here, the pressure, is the pressure difference across the piston. And this because on this side we will have atmospheric pressure, and on this side we have this pressure. So the P that we will use here should be the difference across the cylinder across the piston here. So P is the pressure difference across the piston, and maybe approximated is the cylinder gauge pressure. So that is the absolute cylinder pressure less the atmospheric pressure, because the pressure in the crankcase will often be the close to atmospheric pressure here. Because the pressure on this side is close to atmospheric pressure, so this P should be equal to the absolute minus the atmospheric pressure. And now if for this analysis we are ignoring the mass of the connecting rod, then the line of action of the force F1 exerted by the connecting rod must act along the line joining the center of the big and small end of the rod. So this means that it should be along the line of the connecting rod here. And also if the cylinder is well lubricated, then we can neglect the friction without introducing a significant error for our purpose. Because the piston is often very well lubricated, so you can ignore the friction forces here. Okay, so now if we consider this free body diagram of the piston here, and now we want to calculate F1 and F2 on the piston. So to calculate F1 and F2, first we will use these equations. So summation of all the forces in y direction equals 0, because these the piston is moving only in the x direction. There is no motion in the y direction. So therefore, summation of all the forces in y direction equals 0. So if you consider this equation here, so what we will get? So in the y direction, you have this F2, which is positive, and then you have minus F1 sine of phi here, and then this should be equal to 0. So this is our equation 1. And now to calculate the because we don't know, there are two unknown in this equation here. So we need another equation, and another equation will come from summation of all the forces in x direction. But now in x direction we have acceleration, so then it will become mx double dot or ma. So this is Newton's second law. And now if we use this equation here, so which will become f1 cos of pi, which is one of the force in the x direction, and and then this should be equal to uh, okay, and then another force is this pa here. So pa equal to mx double dot, and now from here we can calculate f1. So f1 will become equal to mx double dot plus pa divided by cos of this angle here. So this is our f1, and we can say that f1 is equal to f divided by cos of pi here, and we can call this equation 3. And here f is we are calling this mx double dot plus pa is f. If you call this f, so then this equation f1 become equal to f divided by cos pi here. So now from here you can calculate f1, and now if you know f1, so then from equation 1 you can calculate f2. So if you use 3 or equation 3 in equation 1, so it will become equal to f2 equal to f1 sine of pi here. So if we just put the values of this f1, so which is f divided by cos pi, and it is sine pi here. So sine divided by cos become tangent. So f and f is this case here. You can call it mx double dot plus pa into tangent pi here. So in this case, or you can call this equal to f. So f2 become equal to f tangent pi, and you can call this equation 4. So we have these equation for the f1, which is f divided by cos pi, and f2 become f tangent phi here, while f is mx double dot plus pa. Okay, so now these are the forces that you can calculate on the piston. Now if you are interested to calculate the forces on the connecting or on the crankshaft here, so we can now draw the free body diagram for the crank and piston together. So this was the free body diagram for the piston. So we had this pa, x double dot was in this direction here, and f2 was f tangent theta here, or pi, and this was f cos pi here, f1 and f2. And now if you consider the crank here, so which is this is our crank. So in this case, this f1 which is acting here, again the same f1 is acting here. So this f1 should also act on the crank, and in this case this r is the is the radius of the crankshaft here, and again we know that theta is equal to omega t here, and in this case, because this angle is pi, and we know that this line is perpendicular to this line here, and this line is perpendicular to this line here. So the angle between these two lines is pi. So this angle also become pi here. Okay, so if you just draw a perpendicular here from this point O, which is the center of the crank. So this OC is the perpendicular on this line here, and OD is just the this horizontal or vertical line here. So now again, if you have this F1 in this direction here, now similar force will be exerted by the engine frame on the crank, and it will be in the same direction as this force here, and this should be equal and opposite to each other. So F1 is again in this direction on the crank. So this means that crank is exerting force F1 on the engine block or the engine frame, and the engine frame is exerting the same force F1 on this point here. Okay, so in this case, now uh, we are also interested to calculate the torque uh, which this engine will produce. So in this case, to calculate torque, what is the torque is just the force times the perpendicular distance. So in this case, the perpendicular distance is this OC here. So if you want to calculate the torque of this F1, which is rotating this crank, so this is the output torque of the engine. Now, if you want to calculate this torque, so it will be just this force times the perpendicular distance between this point and this point here, this force here. So the perpendicular distance here is OC. So OC is the perpendicular distance here, and as you can see, this is F1. Uh, so F1, as you can see here, is F divided by cos pi, and OC. Now, as you can see in this case here, that the OC divided by cos pi uh, is uh, is is equal to this OD here. So if you consider this triangle here, if you consider this triangle here, and if you see this triangle, so then the so OC is equal to OD cos pi, or you can say that the uh, OC divided by cos pi is equal to OD here. So this means that if you replace this OC divided by cos pi by OD, so the torque will become equal to F into OD here. So OD is this distance here, this point here. Uh, okay, so this is the and this is our F now. Now in this case, you can also write that because that OD, which is this distance here. Again, you can also relate this OD to this X here. So if you consider this big triangle, the ODB, so this was in triangle ODC. And now if you consider triangle BOD, so in triangle BOD, if you want to calculate the tangent of the pi, so tangent of the pi will become equal to OD divided by X here. So this means that we can replace OD with X tangent pi here. So this will become F times X tangent pi. And again, you can see that this F tangent pi is just F2. So you can also write this in terms of F2 here now. So F2x. So you can also calculate torque in terms of either F1 or F2 or either F. So this is just the some form of equations for this specific case. Okay, now thus the instantaneous output torque T due to the gas pressure and taking into account the need to accelerate the piston can be calculated from any crankshaft angular position from the knowledge of these things. So as we know that T is equal to F2x, which is F tangent pi x, and we know that F is equal to PA plus mx double dot and tangent pi x, and we know that x is equal to x is the position, and we calculate the value of the x earlier, that x was r cos theta plus q minus 1 over 2q sine square theta. So this means that the output torque of the engine depend on the P, A, M, which so P is the pressure in the cylinder, A is the cross section area of the piston, and M is the mass of the piston here, and in X we have R, which is the length of the crank, and Q is the length ratio of the connecting rod and crankshaft here, and theta is any angle. So this means that the instantaneous output torque. So if you want to calculate the output torque from an engine, which is very important thing, and then you will, especially in the second year, you will try to calculate these things. So due to the gas pressure and taking into account the need to accelerate the piston can be calculated for any crankshaft angular position from the knowledge of. So what you need to know, the piston acceleration, which is this x double dot, instantaneous pressure difference P across the piston. So you also need this P here. The slider crank geometry. So the slider crank geometry means R, Q, and theta, and then the mass of the piston, which is M here. So if you know this parameter, you can calculate the output torque. And note that the instantaneous torque output may be positive or negative, depending on the pressure in the inside the cylinder, and also depend on the other parameters. So this is a typical torque diagram for a four-stroke engine. So if you plot the torque, which is the Newton meter, on the y-axis, and you put the angle, the crankshaft angle, on the x-axis here, so then the output torque will look like this. So again, you can see that this is the working stroke or power stroke, and this is the exhaust stroke, the suction stroke, and the compression stroke. And again, you can see that during the power stroke, you have the maximum output torque, and then in the exhaust stroke, the torque is going to negative and then positive, and then in the suction stroke, again it's positive and negative, and in the compression stroke it's all negative. um, so this is how the output torque from an engine will look like. Now the final topic that we want to discuss is so in the previous case we calculate the forces on the piston on the connecting rod, and we also calculate the output torque from this equation here. But now we want to calculate, or we are interested to calculate the forces on the engine frame here. So this is the engine frame. You consider this ideal geometry. So this is the cylinder, and then this is the crankshaft center here, where the crankshaft is attached, or a bearing of the crankshaft. So as you can see here, you can just consider that the force on the piston was PA. So similar force is also applied on the cylinder here. So the net force due to the gas pressure PA. So again, the same force will be applied here. And again, there was this force F2, which was exerted by the wall on the piston. So now a similar force F2 will be exerted by the piston on the wall. So it will be the same force in the opposite direction. And as you can see here at this point here, uh, this F1 was the force of the frame, which was exerted on the crank. So a similar force will be exerted by the uh, by the crank uh, on the frame here. So this F1 is the force of the crank on the frame, so which is opposite to this force here. And again, the direction of this force is exactly the same as the direction of this force, uh, but it's in this direction here, and it's in this direction here, just in the opposite direction. But otherwise, the angle should be the same. And again, we can split this f1 into two components. So this will be f1 sine pi, and this one will be f1 cos pi here. So now we can calculate these forces. So if you want to calculate all the forces in the y direction on this engine frame, so you will say summation of all the forces in y direction. So in y direction, you have this f2, which is in the negative direction, and you have this f1 sine pi, which is in the positive direction. So if you write f1 sine pi and minus f2. Okay, so in this case, you know that f1, which is this here, is f divided by cos pi. And again, you can see that f2 here is f tangent pi. So in this equation, this is become f tangent pi minus f tangent pi. This means that it's the same. So this means that it's 0. So this means that there is no resultant force in the y direction on the engine frame, uh, because we just calculated and it's equal to 0. Now we want to calculate the forces in the x direction here. So summation of all the forces in x direction. So in x direction we have this PA. So PA is in the x direction, and we have this this f1 cos pi minus f1 cos pi here. So if you just simplify this equation, so fpa and f1 f1 cos pi is this one here. So f1 is equal to f divided by cos pi. So this means that f become equal to f1 cos pi. This means that this become equal to minus f here, and we know that f is equal to pa minus this is equal to pa plus mx double dot. So from here, what we calculate is that summation of all the forces on the engine frame in x direction is just mx double dot. These are so that is there is a resultant force on the frame in the positive x direction, yeah, because this is positive. So there is a resultant force so there is a resultant force on the frame in the positive x direction, and again, there is also and there is also a resultant unbalanced clockwise couple on the frame, which you can calculate from here. So we know that this f2, because all other forces are passing through this center here, but we can take this f2, and then you can because the distance here is x, so this out of balance force here is f2 times x here. You can simplify this. So f2, you can put the values f tangent pi and x here. So or you can write it that t will become equal to f times od. because this x tangent is obviously the OD that we calculated previously. That's why you can calculate the output torque here, or the torque which is here on the engine frame. Okay, so if we just summarize this lecture here, so we introduce the slider crank mechanism. We discussed four-stroke engine and two-stroke engine briefly, and then we drive equations for the displacement, velocity, and acceleration here. Again, these equations are not correct because of some problem with the iPad. So you can see that cos theta plus q and minus, and then you have sine square theta. So this is the first equation, and then x dot become equal to uh, minus omega r and sine theta, and plus 1 over 2 q sine 2 theta here, and then x double dot is equal to minus omega square r and cos theta plus 1 over q cos 2 theta here. These are the equations for the x dot and x double dot of the piston. And then we also discussed about the kinetics of the slider crank mechanism. So we derive the forces on the piston, which is F1 is the force of the connecting rod on the piston. F2 is the force of the uh, cylinder on the piston, and PA is the force of the pressure on the piston here. And we can calculate these values using just equilibrium equations. And then we also calculate the forces on the crank, and we also calculate the output torque of the engine, which is T is equal to F1 into this perpendicular distance. And finally, we also calculate the forces on the engine frame, and we calculate the Fx, which was PA minus F1 cos pi here, and which was PA minus F, which was equal to PA minus PA plus MX double dot, and the summation of all the forces in x direction was just equal to MX double dot here. So this is the and this is the how the free body diagram of the engine frame will look like.